Kia ora koutou, ko Andrew Sargent, tōku ingoa. Today we'll be running through the Scholarship Chemistry webinar. It's my pleasure to introduce to you Dr. Suzanne Boniface. She will be going over, I think this is an exam approach, last weekend or last Friday, I believe. She covered the skills approach to scholarship physics. I have put in the chat the link to that. I have also put in the description of the video, of this video, the link to the paper that she'll be going through today. All these webinars are brought in partnership with Study It. So at the end of this tutorial, if you have any questions, you can also go to Study It and ask them. And there's also a wealth of resources there. Also in the previous video that Suzanne run is the link to all the notes. So I haven't put them in the video of this description, the description of this video, but they are in the other video's description. Other than that, without further ado, over to you, Suzanne.
Cool. Thank you very much. And welcome to you all from me. I hope you've had a good sleep and recovered from yesterday's Level 3 exam and that you're raring to go now with your step up to scholarship. What we're going to do in this webinar is we're going to focus on the approaches that you take to questions. I mean, there's really no point in me just going through and answering last year's questions for you. You can do that for yourselves. But I want to talk to you about how you approach the questions, and we'll use last year's questions as a guide. So it might be helpful if you've got a copy of last year's questions in front of you, but you can always come back to this presentation and think through and look at the questions afterwards. Actually, I'd suggest you do that. If you find there's things that we come across today and I go through them too quickly, or you just can't get your head around them at the time, make a note. And make a note about how far into the 2 hours we are, so that you can come back and go through just the specifics that will be helpful for you. It is a 2-hour webinar. We're going to try and get through a 3-hour exam. You are welcome to ask questions in the chat. And I will pause briefly in between each question so that we can maybe collect some of the things that are troubling you from what I said at that time. And also after an hour, we'll just take a very short break just so we can get up and walk around and kind of get a little bit more oxygen in our brains. I think I'm probably going to need that as well. Through the slides, what I'm going to do is give you my ideas about how to approach the questions. And obviously, there's lots of ways that you could do this, but it does help to have a plan to fall back on. And you might detour a little bit from it, but going in with some ideas about how you might approach questions will just relax you a little bit and help you feel more confident about what you're going to do. Okay, so I've called this Stepping Up to Scholarship Chemistry, and my first question for you for the day is, what are the differences between scholarship and Level 3? And I just have to move something so I can see what I'm saying. And I hope that your answer will be something like, it's not what you know, because you just have to know your Level 3 chemistry really well. It's what you need to be able to do with what you know. And if you look at the standard, the chemistry standard, and if you have had an opportunity to engage with the material that I put up last week about skills, what the conclusion I came to for you was that in the scholarship exam, 3 of the key things that you need to be able to show is an understanding of the world from a chemistry perspective. You need to be able to show logical, concise, clear, convincing communication, which means you need to be able to understand the world from a chemistry perspective and be able to explain it concisely. You also need to be able to show problem-solving skills that use chemical principles. And here's a quote. So this is what you're aiming for. Just keep it in mind. You may not all be aiming for outstanding performance, but you're still trying to demonstrate planning, processing, linking, and applying chemical principles across all areas of chemistry to solve problems or provide explanations of observations from a chemical perspective. Now, the words that I really like here are planning, processing, and linking and applying chemical principles. There's got to be an element of planning if you're going to get through what you need to in the 3 hours. I've put up a slide here with hints from past examiners, and I've colour-coded this to link back to what I had on the previous slide, because what the examiners say support that. Here you have to be you have to be familiar with all your level 2 and 3 chemistry. That's a given. There's a lot in what the examiners say about communication, about a clear understanding using the language of chemistry, about being logical and coherent, about correctly using chemical vocabulary and defined terms, providing explanations that are appropriate to the question rather than just being a brain dump. Hey, a brain dump is actually okay if you can't answer the question because it'll give you some points, but we'll come to that in a minute. And answers that are supported by balanced equations or correct formulae. You may not always be told in scholarship to do that. You are at level 3. You have to know that that's how you communicate in chemistry. And then there's something about the kind of problems you're going to have to solve. And we dwelt on a method for that in the skills webinar. You might like to come back to that. But I'm actually going to use that today because it now has become my way of problem solving. Will you take to heart, please, before we go any further, this last pink one here? Because this is actually something that you need to remind yourself about, that your calculations need to be logical and clearly laid out. They have to be able to be followed by somebody else who can't necessarily see how you got from A to B to C if you don't tell them. You will find the calculations often in scholarship require more steps than you might have had at level 3 or level 2. They'll be similar, they'll use the same equations, the same mathematical formulae, but the way you put them together will require a lot more logical thinking than you might have had in the past. So you need to show clearly to the examiner how you got from A to B to C, just in case you made a silly mistake along the way and your process is perfect, because they can then give you credit for what you've done. Okay, so let's take just 3 slides to remind you about the 3 key skills. Understanding the world from a chemical perspective, and a nice way of packaging this is that we have our 3 dimensions of chemistry. We have the macroscopic that we can see and measure. We have the submicroscopic, which is the dimension that we find our explanations in. So it's what's going on in particle land that explains what is going on in the world that we can observe. And then we have our symbols, and that really saves us a lot of words. But it's not just that, because it's not just a shorthand. There's so much in the symbols that actually links back to what we're seeing at the macroscopic level and using the submicroscopic to explain it. A very, very quick illustration. Liquid water, so familiar to all of us. What does it look like at particle level? Well, here's a way of kind of explaining it. It helps us think about the nature of the particles, the water molecules, but also how they're interacting. You know, one year I put these all in lines and then realized that I picked up the wrong picture, because even though the particles were right, the way they were interacting didn't match liquid water. And our symbols, we put an L in to say that it's liquid. Meaningful to chemists, but maybe not to a lot of other people. So you've got to take that on board in your explanations, partly because we need to actually show how we put all these things together. But also you'll find that often, as soon as you start to think about the particles, the explanation for what's going on starts to make sense, but also the symbols can help you with your explanations as well. So our communication, we actually need to link our observations to the natural interactions of the particles and the symbols. So a chemistry essay must have some symbols in it. If you're chemistry literate, it shows. But you also need to have a plan. One of the biggest problems for me when I used to mark these kind of exams was students going round and round in circles, saying far too much, getting themselves lost in the middle of it because they did not stop and think about how they were going to put their explanation together. So start off by saying what you're going to be talking about, what the chemistry idea is, what's the connection the link between the chemistry idea and the data that you're explaining, and then have a really good discussion that's very easy to follow that links back to what you said there. And that's the kind of explanation that you're used to at level 3. The problem solving. What do you do when you don't know what to do? And so often in a scholarship chemistry exam, you won't know what to do straight away. You might have to stop and think, read between the lines, pull out all the chemistry ideas, and then how you're going to actually answer it will emerge if you've got a plan for getting into all those words that they put on the page. So step 1, what actually is the question I'm trying to ask? In the midst of all those words, where's the one-liner that says what I have to solve? What data am I given? Can I pull all the data? And you'll see this in one of the questions from last year. Can I pull all the data off the page of words and make sense of that? And once you've done that, you've got a plan. You can see where you're going. You can implement your plan and you can check out your answer. Okay, you won't need to do this to answer every question. This is what you do when you're stuck. But if you haven't practiced it or thought about it, then when you're stuck, you're stuck. So here's a way into things. All right, let's take a look at last year's paper. Here's what it looked like, front page when you get to the exam. Take a note. You've probably seen lots of these papers, some of you who've already sat several scholarship exams this year. Time allowed 3 hours, that's a given. Total score 32, probably the same for many of the science and maths-based exams. So what does that mean? 4 questions, 3 hours, 45 minutes a question. So aim to do each question in about 35 if you can, and that gives you time to come back. Now, it is really important that you don't get bogged down in any particular question and that you do have time to get to the end of the paper. And we'll come back to that when we look at this year's paper, because one of the best questions was the last one. So don't take up too much time getting bogged down. Move on so that you've got a chance to try everything. And that will be a mantra, try everything. The other thing about scholarship chemistry, and again, if you're familiar with the other science and maths-based ones, the questions are often broken down into smaller parts. So you don't just have to think, oh, I've got 45 minutes for this question. It's kind of, I've got 3 parts to this question, and I don't want to spend the whole 45 minutes on part A and miss out on B and C. Last year's paper, there was only 1 question of 2 parts. All the others were 3. Okay, what do the marks mean? Why am I dwelling on this? Why do I think this is important? Because what you've got to do is get into the top, I don't know, is it 250 students in New Zealand in scholarship chemistry? So you want to gather marks. You don't just get marks for your good scholarship answers. You get marks for everything that you write that's sensible. You can even get 1 if you show a meagre understanding relevant to the question. Doesn't mean you can answer it. It just means that you know they're related chemistry. And obviously, as you show more links to the actual question, you're going to get more marks. So all but 1 of the last, I think, 5 years, the scholarship score has been 17. Okay, so that's 1 question that you have answered up for 5 marks, and then you've collected enough marks to make it up to 17 across the other, with the other 3. Okay, so hear this, please, and keep it in mind when you go into that exam. Attempt to answer all questions. If you can't solve the problem or explain everything, at least write down what you know about the related chemistry. So there needs to be something in every question. So what we're going to do as we go through the questions today is we're going to actually look at them and try and find out what chemistry is involved before we start trying to answer it, because that will actually lead you in the right path, even if you can't get to the destination. Okay, here's last year's paper. Remember, you also get a resource booklet, and the resource booklet for last year had some spectra in it. You've got your spectroscopy data sheet, and you also have a periodic table of the elements. Please take note that at scholarship, you're not always given molar masses. It's a real hint, isn't it, sometimes at level 3, when you get a molar mass, you know you need to use it to compare something or for a calculation. You might have to go looking for it here. But at least you know where to go. You've got your resource sheet. Okay, so let's start with question 1. How are we going for time? Okay, right. See if we can get through this in half an hour or a bit less. So what I've done initially here is I tried to put the whole question on a page just to give you an overview of what you're going to be looking at in that first maybe 45 minutes, depending on how you choose to do this. You might find it better to just skim through the whole exam in the first 5 or 10 minutes and take a note of the questions that you're most, or the areas of chemistry that you're most comfortable with. So I mentioned to you that I thought the best question was the last one. The very last question last year was the spectroscopy one. So if you're really good at that and you really like that kind of problem solving, maybe you should do it earlier in the exam, so that you can solve that, get it out of the way, and then focus on things that you need to spend a bit more time with. So here's question 1. It's divided into 3. When we come to look at it, we may find that it almost looks like 3 even parts. So that's only 15 minutes for each of these. I haven't here put the standard electrode potentials actually on this page. They were embedded in the question this year. Some years the electrode potentials have actually been in the resource sheet. Okay, so because we're limited with time, I'm going to move through these ideas, the things I would do fairly quickly. I hope you can keep up with me, but you may not have time to read everything. You'll have to take my word for some of this. So as we look at this first question, we've got calcium metal. Oh, hang on. Yeah, we've got calcium metal. We put it in a beaker. So here's another hint. Kind of try and find the story behind what's happening. We talked about the macroscopic. What's actually going on here? Can I develop a little bit of a storyboard for this question? Because that might then help me to move into it. We have calcium metal. We put it in a beaker of distilled water. It reacted. We got a colourless gas, and we've ended up with a colourless solution. We threw in some more calcium metal. We know the mass of how much we've got in there. And now we've got the same gas, but we've got a cloudy solution. A cloudy solution. Yeah, a cloudy mixture there. And then after we got that white precipitate, we added some hydrochloric acid, and it became clear. Now, already you're starting to think about, where do we learn to do this? We're given a KS. So we're told about equilibrium principles. We're given KS. So this must be about solubility and precipitation. So that's already focused you on the kind of calculation that you're likely to have to do. We look at the next one, and the thing that probably stands out is that we've got standard electrode potentials. So and when we read it, we've got a whole lot of reactions, and we're going to have to justify those reactions. So it's about spontaneous redox reactions. We look at the third one, and the word that stands out straight away, buffer solution. And we get to the end and we find out that we have to calculate pH. So we've already got an overview of this first question, and if calculating pH of buffer solutions is not your thing, then move on. Don't get bogged down by it, but do come back and write down what you do know about buffers. Sorry, I'm forgetting my words sometimes, but yeah, so let's move into it. I will say that I have never seen a scholarship exam without a buffer calculation in all the years that they've been there, so do make sure you can do the basics. Right, let's look at question 1. And I've got 3 words on the side here, which is how I'm going to delve into the question. And as I said before, I've got into the habit of doing things this way. And sometimes you might find this helpful. Other times you might be able to just read it and the answers will just flow out for you. So what are we trying to do here? Okay, what's our aim? Well, let's read it and see. We've got a reaction of calcium metal. We've already said this. We've got precipitation. What does that trigger in my head? If I've got a precipitation, then in my equilibrium system, or in my system, actually it's not at equilibrium, Q is bigger than KS. So I'm already thinking about where I'm going into this. I've dissolved a precipitate, so that means I've got to have some discussion about equilibrium principles. Okay, so let's come back to that. Now, when I go to analyse this and to try and pull out the data, it's really helpful to develop the words into equations. Because as you do this, you'll start to see the connections with the things that you already know. So I've just written the equation for calcium with water. I've assumed that the gas was hydrogen and that I made calcium hydroxide. You were asked for balanced chemical equations, but the key thing is that you recognise that calcium hydroxide was made. The other equation that's useful in terms of linking it to the information you're given is the dissolving reaction, the equilibrium reaction, because we know that that's going to link to Ks. I'm given Ks. How about I get the expression for Ks in here? Because that pulls it out of all the words and links it to the actual Ks expression. What else do I know? Well, there's 3 things that happened here, and I've got to justify those 3 observations. So the first one, I put that much calcium in, that much water. And what do I know? No precipitation, so Q is less than Ks. The second thing was I added some more. Okay, so I've just realised that so I've added some more calcium. I added 0.396 grams to the solution that already had 0.185 grams. So now I've got a precipitation, so Q is greater than Ks. Okay, and the last thing was that I added some HCl and the precipitate dissolved. Now, you've really got a plan here now sort of emerging, haven't you? Because firstly, you can see that here you've got to prove this. Secondly, you've got to prove this, and you've got this Ks expression here. And then lastly, you've got to figure out why the precipitate dissolves with the addition of HCl. But if you've already written your equilibrium equation, you know how you're going to answer it. So we may not even need to go through all the answers today, because if you've got a plan and you've got your level 3 aqueous hat on here, then you can probably see the way it's going to go. Okay, so what would our plan be? Well, we're going to do this comparison, but let's just remember that we were asked not just to show these things, but we were asked to use them to justify our observations. Very often in scholarship, you will end up doing a calculation, and it might be complex, and you might be so relieved to get to the end of the calculation that you forget about what you were supposed to use the calculation for. So just make sure when you're doing your planning and you're thinking that you remind yourself somewhere, you highlight it somewhere, that you've got to come back and do that. And don't forget that when you get to when you've done the 2 calculations, that you have to do the third thing. Okay, what I do want to just say is that the answer that I'm going to give you patterns the one in the NCEA, in the answers, the answer schedule. But when I first did the answer to this, I actually calculated solubility, and I compared the mass added to the actual solubility, which was a different approach, and it came up with the same kind of answer, and it was quite acceptable. So if you chose to go the solubility way, it's okay. You just won't find that I've written the answer for that. Okay, so on this page, what I've done is I've just repeated what we've got here, and I'm going to go fairly quickly through the implementation and just try and show you how this is just slightly requires a little bit of different thinking from how you might have approached your level 3 answer. So I'm just dumping it all here at once for you so that you can see where we're heading with this. But remember, we write our expression, and then what we've got to do is actually find out these concentrations. So there's just more steps in the pathway to find the concentrations than you might have had in the past. So the only thing you know is the actual mass of calcium. So you can use the moles expression to find the moles, and then you can use the volume you've contained it in. So you should be pretty good at these kind of calculations. It's the difference is that you have to recognise how you're going to use them. So there's nothing really different from level 3 in the calculation. It's how you put it together and see what you have to do. In the second one, we're actually going to go through the same kind of calculation. What we're looking for here is that our Q, and remember, Q, it takes on the same expression as Ks, but the actual number, the value of Q, will show us whether we're at equilibrium or not. And then in the third instance, we're going to explain why the precipitate dissolves on the addition of hydrochloric acid. And so then we need to come to our equilibrium reaction, and we need to use equilibrium principles. I think here, again, work from your equations. So you've got your equation here. You then write the equation for the reaction of the acid with one of the products of the equilibrium system, and then you can discuss how that changes the position of the equilibrium and therefore dissolves it up. Okay, so we're going to have to move on to the next one. And if you've got some queries about that, then you can put that into the chat. Okay.
Just one query, if that's all right.
Yep, sure.
Someone asked, how did you get the first equation? I assume that's the top line.
This one here? The equation or the reaction.
How did you do?
Right, so if we go back to the words, I've developed that from, hang on, I'll just go back there into the question. So I've developed that from the story, if you like, of what's written here. So calcium with water, and it reacts to produce a colourless gas and something else. So we've got a pretty, if you're not familiar with the action of a metal with water, you think about the reaction of sodium with water, that's the same kind of thing. If you're not familiar with all of that, go as far as you can just by following what it says. So I put calcium with water, and I made calcium hydroxide. I had to, because that's what the question's all about, and then kind of try and work out what's left. But a colourless gas is quite likely to be hydrogen. Okay, so again, it's actually developing the equation from the story that you're given, from the observations you're given. And actually, that's something that's going to happen in the next one as well. So come back in the chat if that wasn't what you were after, and we'll see if we can address that a wee bit further down the track. Okay, so this is part B of the question. And this time what you'll notice is that I've included the electrode potentials. Now, a couple of comments here. This is not necessarily the way that you will have been given the electrode potentials in when you did the level 3 redox internal. Often you're just given a series of E0 values, and instead of being given the equation, the oxidant and the reductant are just given in brackets after the E0 sign. And sometimes I've found that students can get a bit confused when they don't have to develop their own equations. And the reason for that is that all the equations that you're given here are reduction equations. That's because it's a reduction potential. So the main thing here is it's actually helpful because you're given the balanced half equations, but when you come to use the E0s, just keep the sign that you're given in this list here and use it in the way that you've always used the E0 equation. So I'll show you what I mean when we come to that, but I just don't want you to be thrown by a different way of being presented with this data. Okay, let's take a look at the question. We start off with a pale blue acidic copper chloride solution. And again, be thinking in your head about what you would see, but also be thinking as you read it, how you would develop the equation. Okay, so we've got the solution, and then we're told how it was prepared, by copper metal in chlorine water. And then we add some aluminium foil to the sample of the solution, and the foil disappears. So it's a series of reactions here. And then we also added some potassium permanganate to a separate sample, and this time we got a brown solid and a pale green gas. So already in your head, you're thinking about what these things might be. Pale green gas might have triggered for you that it's likely to be chlorine. What do we have to do? We have to use the potentials. We've got them given to us. Again, we've got that word justify. Justify the reactions with the use of balanced chemical equations and cell potential calculations. Wow. If you look back at the early papers, you were never given that much guidance. So that's really helpful for you. So what are we going to do here? Let's check it out. We're going to justify the redox reactions. How are we going to do that? Let's get it down here first. We're going to look at, you're possibly writing E cell here rather than, it does say cell potential, maybe cell is better. And this is my way of doing it because it's helpful in my head that's the reduction half equation, the reduction half cell minus the oxidation half cell is greater than 0. So we're going to use these numbers once we've identified what is the reduction one in a given reaction and what is the oxidation one. And we're going to keep the signs the same as they are there. We have 3 reactions. Now, I actually find it quite helpful to just change the words into symbols. And you may not, and you'll notice here that maybe you have, but you don't necessarily have to have balanced them as you're going. All right, I did, but you could just write down just in your own mind what's going on here. Have I got symbols? And then you can go and spend a bit more time balancing them the next time through. So what I'm talking about is unpacking the question and then developing your answer from there. So what would we do? You've done it before. but you may be a bit rusty on it because it wasn't internal. First one, here's my equation. I've balanced it. I've picked up the two appropriate half equations, and this is a relatively easy one, isn't it? Because you've got 2 electrons on one side and 2 electrons on the other, so it's quite straightforward. And then what did you do? You took the E0 cell, if you prefer to do that, perhaps you should. And then we've recognized that chlorine is being reduced and that copper is being oxidized. See, this is the way that you've probably had those potentials presented to you in your level 3 internal. Okay, put in the numbers, it's greater than 0, so we can say it's spontaneous and that's why the reaction occurs. And we can just go through and do that with all of them. What you needed to recognize with this one is that there are 2 things going on. In the second part, you've got your aluminium, which produced a colorless gas. And then you've also got your aluminium that reacted with a copper 2+ and gave you copper metal. So you're having to work out for yourselves what the possible products are based on the description you've got here, but also based on common sense, because there's only a limited number of reactants and products that you could possibly have. So here, again, you're just coming up with the fact that you've got a positive E0 for the overall reaction, for the cell reaction, and that this is why how you can justify that these reactions occur. So it's really more of the same each time in this one. There's not a major difference. I guess the big thing that you have to do is figure out what the reactants and products are before you can show that you know how to justify a spontaneous redox reaction. Okay? All right. The last one, the buffer one, the last part of question 1, just to see how we're doing for time. Right, we're getting there. Right, a buffer. So, obviously with this one, what's it all about? It's a buffer calculation. A buffer solution with a pH 10 was required. The procedure used was starting with methyl ammonium chloride. We know the volume that it was of the methylamine solution that it was dissolved in. And then we have to figure out what the pH was. So we're told that it was too high. It wasn't 10. Okay, it's above 10. And so there was an attempt to lower the pH by adding some hydrochloric acid to the solution. So you're asked to calculate the pH of the final and the initial solutions. Okay, so it's pretty good when you get there. And then decide whether the technician had added a sufficient amount of hydrochloric acid to achieve the intended pH. I must admit that the first time I did that, I forgot to do that last bit. So that's why I wanted to just make sure you remember to come back and do it. So you're given a bit of information here. You're given the pKa of CH3NH3+, and you're given the molar mass of the methyl ammonium chloride. So if you're not very familiar with these particular compounds, then just take a note that you are familiar with ammonia, NH3, and you're familiar with ammonium chloride, which would be NH4+. So these are really useful compounds in terms of making buffers. And so don't be thrown by being given chemicals that are unfamiliar. Try and link them back to something that you already know. So I've got here to calculate 2 pHs. The first pH comes from a buffer solution made by dissolving one of the components in a solution of the other. The second buffer solution is made by taking a buffer solution and adjusting the pH by adding some acid. So there's a little bit of thinking about logically what's happening here. And then you will find that the calculations are not really too unfamiliar once you know where you're going to get the concentration of the species involved. Okay, so I'm just going to go through and now pull out from the words the things that I think are important and useful, and you will have all sorts of different ways of doing this for yourselves. But again, if you don't actually have a plan for getting into all the words, here's a possible way of doing it. So my initial buffer, I know the mass that I've started with, and I also know the molar mass for that, so that links to moles. And I know the volume of this that it was in. And the important thing here is also the concentration of the methylamine solution. It's helpful to write the equation for the buffer. It's really the equation is for the reaction of the acid in water to create the base. But this time, of course, both the acid and the conjugate base are involved in the mixture. That's why it's a buffer solution and why the concentration of each of these species is really important. For the second, and then the other thing that might be useful to actually have there as part of your thinking is what's the relationship between the components of the buffer solution and the pH, because that's what you're having to do. So there's two ways of doing this. You can work, if you're not sure, you can't remember this, you can take this equation here, this equation for the reaction, and you can generate the Ka expression, and you can rearrange that to get the H3O plus concentration. So if you're not very good at remembering the mathematical formulae, you can develop this very quickly from first principles just to be confident that you've got it round the right way. So then once we've got we know the Ka, and you'll notice here that I quite like working with not the whole number for Ka, but the power of 10 from the pKa. I just find that a convenient way of doing it, but that's up to you. You do it how it works for you. And then you can link that to pH. Some of you might use the pH expression, pH equals pKa plus the log of the base over the acid. So that's fine. You just figure that one out for yourself. The final buffer. Okay, this time we know the pH of the initial buffer. We actually know the concentration of each of these components, but we're going to change those by adding HCl. So our thinking is we have to figure out how the concentration of each of these have changed. So just keep in mind that when you're dealing with a buffer solution, the pH is totally dependent on the concentration of the acid, of the ratio of the acid to the conjugate base. So I'm going to calculate the moles of each of these in the original buffer and use it to find pH. Then I'm going to calculate how the changes and use that to calculate the second one. Okay, I've got something random on the screen there. So there's all the things that I put on the previous page, and I will walk you through this because I know some of you do find that aqueous chemistry a little bit of a challenge. So let's have a look at it. First thing, I said that the first thing we had to do was that we had to work out the concentration of each of the components. But what you'll notice here is that I've kind of skipped a little bit. I've worked out the moles of each of these, and I haven't converted it to a concentration. And the reason for that is what it says on the bottom of the screen here, is that the volume in which these species are contained is exactly the same. So I could divide both of these by the same volume as an extra step, but I don't need to, because within that volume, the mole ratio is what determines the pH. So I can leave that step out. So now I can substitute in, and you'll see that this is the convenient way I have of doing this. I'm not using the Henderson-Hasselbalch equation. I'm going to do it from this one, but the other way is perfectly acceptable. So there's a level 3 calculation for buffer pH. You just had to get these concentrations for yourselves, one from the mass and the other from, you had to get the moles for yourselves, one from the starting mass and the other from the concentration and volume within the solution. Okay, that was the first one. Second one, what's going on here? Really helpful to write this equation out for yourselves again. So however much methylamine I had, some of it reacted with the H+. So this has dropped and this has gone up. Okay, so I've created, in the process of adding HCl, I've increased the amount of conjugate base, decreased the amount of acid. So that's quite useful, isn't it? Because it does mean that the pH is going to go down because I've made a bit more acid. So keep thinking about how what you're doing at particle level is reflected in what's going on at the macroscopic level. So step 1, how much H+ did I put in? How many moles? Step 2, how do I relate this to what's changed in the solution mixture? So I can look at the moles that I had of my original buffer. Can you see that that's the moles I had up here? I don't have to recalculate. I can just go back and pick that out, subtract that from it, And what I find is that the moles of my base, that's dropped as expected. What's happened here is that the moles of the methyl ammonium ion that I started with has gone up by that amount to this. So now I've got a new mole ratio. I'm going to put that into exactly the same pH equation, and I'm going to come up here with a pH of 10.05. Now, in my mind, that's probably okay. It's pretty close to what he was trying to do, but he hasn't quite got there. So the calculation does show that you don't have sufficient HCl to reduce the pH to that was required. But then it depends, if you're going to round it down to 3 significant figures, then, no, maybe it's 10.1 and not, So it's best to be really quite precise. It does show that there is insufficient HCl. Okay, we've covered 3 areas of chemistry in that first question. It's quite, it's jumping, it's gymnastics, isn't it? Chemical gymnastics, going from one area to the next. So hopefully you're with us and that's okay. Any particular questions? We'll move on to question 2. Oh, I see here I've got the assessment schedule here, just showing you what the requirements were for scholarship and outstanding. I was looking at this with some students yesterday, and we got a little bit confused by the fact that it says 2 of the following. What I wonder if this means is that you have to actually have 2 of these absolutely correct for outstanding, but you may, so that may not give you 8 marks. You might have to get them all right, or 2 of them completely right to get 8 marks, and the third one not completely at outstanding level. I'm a little bit confused by this, that you have to get 2 out of 3. Don't think that means you only have to do 2 out of 3. Okay, you've got to show scholarship level answer in 2 out of 3, but you can collect more points for the other one as well. Okay. And you'll notice here, the scholarship not awarded is telling you some of the things that you could have that could contribute to those non-scholarship level marks that you're trying to collect to get as many as you can. Okay, all right, to move on to question 2. I couldn't get all of question 2 on the same page because there's so many words for part A. And then if we take a quick look at the next one, no, will we do that? Will we do that? We won't. I'm just because I've just got a couple of points as you read through this, all these words, and you won't have time to do it in the short time we have available. But what stands out as you come through here is this equation. Are you chemically literate enough to look at that equation and think, oh, this is a redox equation? It's got permanganate in it. That should help. It's a redox equation, and it means that I can, that'll do. I've got a redox titration perhaps because I've got all these concentrations and volumes. There's another thing going on here you'll notice as you read through, that you've got an acid-base titration going on. And then you can go back and figure out how they're useful. Now, if you can't solve the volumetric analysis question because there's a lot of things going on about what you're using and what you're trying to do with it and all the processes involved, find the titration bit of the question and at least prove that you know how to do a titration calculation. It won't get you a scholarship level answer, but it does show that you know some of the relevant chemistry and you've got the skill to do that. So if you're really daunted by this, do something. And finding those bits of the titration calculations is a good way into it. Okay, so that plus these 2 was question 2. So that's quite a lot to take on board for 45 minutes. You will perhaps notice here this is a discussion question. It's all about entropy. And there was a bit said by the examiner last year about the need for students to actually get their heads around the entropy discussions. And the last one, perhaps not an awful lot to say about molecular shape. So you may find that it's not an even division between the 3 parts of this question. Okay, so let's have a go at looking at this titration one. And again, I would say that I have never seen a scholarship exam that doesn't have a titration question in it somewhere. It might well be a redox titration, it might be a back titration, but there's usually somewhere that a volumetric analysis of some sort is carried out, and that will have a titration calculation in it that links back to whatever it is you're trying to find out. So I will show you how I extracted all of the numbers out of here and got this whole page onto a couple of lines. But we'll just read, I'll just go through a few things that we can pick up, and you might even think about highlighting this on your page. I don't usually like highlighting as the only way of getting the data out, but it might work for some of you. As we go through this, the first thing that we're told was that we have a certain amount of a solution. It's got three things in it. It's got acetic acid, sodium chloride, and oxalic acid. Note that the oxalic acid is a solid. Okay, make a note of that in your head as you come along here. We then diluted. So a volumetric analysis usually has a dilution. I guess that's because quite often students are not very good at it, so it keeps coming up every year. And then a certain amount of that diluted solution was used in a titration with a standard solution where I know the volume and I know where I know the concentration, and I actually have a measure of the volume, and I've got an equation. Okay, then I went back to my diluted solution and I did something else with it. This time I've actually got sodium hydroxide that I'm adding to it, and I'm not given an equation. Usually what I've noticed is that if it's a redox titration, you're given the reaction equation because they don't really want you to spend time trying to figure out how to balance that, because that's not what the question's about. But here they didn't tell you, so that's okay, because it's a simple one that you should be able to figure out. Okay, and then you went back to your undiluted solution and you got some other data from it. So there's a bit of a story through here, and it's actually trying to connect the different parts of the story with the data you're given that will allow a way forward to come out of this. So seeing all these words, please don't be put off by it and think, I'm going to ignore that question and then maybe come back to it. I've got some time. Try and do something with it, and then come back and see if you can complete your answer if you get a bit bogged down. Okay, so here we go. What am I trying to do? Let's keep in mind that just coming up with the result of your titration calculation is not the answer. You're trying to determine the mass of each of those things in the original sample. Now I've called my sample X, and I then got a diluted one. You find a way of tagging what you're doing so that the marker can see their way through your calculation. Please, whatever you do, don't present them with random numbers on a page. Your numbers need to be tagged to whatever it was that was going on in the laboratory, in the reaction. So what was going on? I diluted my original sample from 20 mils to 200. So I've now got that pulled out, and I know that I've got to come back and use that dilution factor later. My first titration, I took the diluted sample and I reacted it with permanganate. How was that useful? Well, I'm just going to put the equation in here, and I'm going to think about what that means. So from my first titration, I've here got my oxalate ion, and that's going to relate back to the amount of oxalic acid that I have present. Okay, in my second titration, I've actually reacted sodium hydroxide with whatever was present in there. And I know how much of the sodium hydroxide, and I know its concentration. I'm going to write the equation because I recognize that the sodium hydroxide will react with the acid there. You've done this. This is your titration, acid base, weak acid, strong base titration. You can link that to other things you know. And now I've got both of these have been useful in determining the amount of oxalic acid and acetic acid. The last thing I need to do is I need to figure out how much sodium chloride was in there. Okay, and all I know the last thing is the total amount of solid present in there. Okay, so from here I can get that, from there I can get that, from there I can get that, and I can make a plan. Okay, I can calculate the mass of the oxalic acid from here. I can calculate the mass of the acetic acid from here, and I can calculate the mass of sodium chloride by recognizing that I have two solids, and that's the total solid, and I've already got one. Now, can you see that is a big chunk of writing from the exam reduced to something that is now workable? By listing it out in order like that, by just going through the story, the actual plan, the method for answering it comes out. So I guess what I'm trying to say is take a few minutes to do this planning. Rather than jumping in at the beginning and figuring out that you know what if you know what you're doing, fine, but jumping in at the beginning and then getting a bit lost because there's so many words. Okay, so here's my answer. I'll just put it out there for you. If you've not had a lot of practice at redox titrations, come back and think about why I've done what I've done. I always step these in, and you see this is what I mean about tagging my numbers. I like to put in the equation that I'm using. So here I'm tagging it that that I'm going to find out the moles of permanganate. This is what I'm using. I, again, think it's really good practice to put in the units because then I'm confident that I've got the right formula here, that it is a multiplication. Here's my moles. Here I've now related the moles of my acid, my oxalic acid, to the moles of permanganate. And if you go back here, you'll see it's a 5:2. That's where I get the 5/2 here. And that gives me now the moles of oxalate iron, which is going to be the same as the moles of oxalic acid. Okay, in the second instance, and then I can then link this back. So you can do this at any point. What I've done here is I've worked out how many moles there are in the diluted sample, recognizing that I only took 20 mils out of my 200. So I can work out how many moles I had in the 200, and then I can work out how many moles I had in the original, because this time I took 20 mils of the diluted one here, and I had diluted that by a factor of 1 in 10. So that's where that number 10 comes from. So there's my first answer. And then you can go through and do the same with the second answer. And this time it's the moles of sodium hydroxide that you've worked out. But what you need to recognize, so this is probably the little trap in here that I didn't comment on before. The sodium, and actually probably I would have been better. And actually I'll go back and fix this if anyone picks up the actual PowerPoint, because of course the sodium hydroxide is reacting with both the acetic acid and the oxalic acid. Oh gosh, I'm sorry guys, I should have put that equation in there. That would have been more helpful. So from here, yes, we can work out the moles of this, but of course we've got to subtract out of that the moles that have reacted with the sodium hydroxide. So I've done that down here. And if you hadn't thought about that at this point here, then you might have ended up with a little bit too much oxalic acid and come to the wrong conclusion. So I guess in a way, it's probably good that I forgot to do that, because it makes you realize that there is a little bit more thinking in here. This is kind of the scholarship level thinking. It was very easy to think about just the sodium hydroxide reacting with one acid without recognizing that there were two in there. Hope you're thinking about this is better than mine. Here we go. This is right down here. So moles of sodium hydroxide is equal to the moles of the acetic acid and twice the moles of the oxalic acid. Okay, that's fairly obvious when I tell you that, isn't it? But did you think to put a 2 there, because for every mole of oxalic acid, 2 H pluses were released. So you've got two things going on here. You already know this. Okay, you've got it in here. And so you can work out the moles of the acetic acid. Sorry, I'm calling it acetic. I should be saying ethanoic. This is a habit I got into when I went back to teach at university. So ethanoic acid, here we go. Okay, so you're with me there? And so then we can go back and find out what was in the original sample. And then from there, we can go to the next one. And here, I've actually done these 2 steps here. I've done them all in that calculation there, just to try and fit it on the page. So go back and do this step by step in your own time and see if you can get your head around the thinking involved there. The last thing we did was we determined the amount of sodium chloride in the original sample, and here we had to recognize that only 2 of these were solids. So when I extracted out or figured out the total solids, it was related to the 2 things that I had here. I already knew how much oxalic acid I had, and so that meant that I could work out how much sodium chloride I had. But what you do need to recognise is that here we've got 21.3 grams, but it's only 10 mils of sample X, and the students were given 100 mils. So the total amount of the total mass that you get from the 100 mils is going to be 10 times that. So there's quite a lot of thinking logically and taking on board all of these little extra bits that makes this quite a big step up in a way from the thinking that you will have had, from the calculations you will have done in the past. So it's the logical thinking. There's really nothing in the chemistry here that is different from what you've done at level 3. It's actually how you're going to use this combination of ideas. Okay, so right at the end we came up. Oh, sorry, did I not? Oh, yes, I did. Sorry, the mass of NaCl is 15 grams. Okay, so that's only a page of answer there, if you like, and it took a whole page to ask the question. So hopefully that's helpful in giving you an idea as to how you can think your way through these questions that come with a whole lot of words. Okay, well, we're running a wee bit behind time, but that's okay because we did a bit of blurb at the beginning and hopefully we can speed up a bit with the others. Let's finish this question off and then take our break, well, at least this part of it. Our enthalpy entropy question. So we know that it's going to be about that. I didn't bring that in here. Let me just go back. Okay, we're going to read out the question, and I've already told you what I think this is about. Because this here is a discussion question. It's not really a problem-solving question, although you do have to think through what the data actually means, and that might be a problem for some of you. But here you're asked to discuss the thermodynamic factors that affect the relative solubilities. So I've actually got some slightly different words that I'm using leading into this question, and that's because it's important when you come to explain something that you don't just start somewhere in your thinking about what this question is about. It's important that you actually start at the beginning. And so I've started to realize how helpful it is to have a plan for your discussion that is a little bit like how you would start an essay, where you begin by saying, this is what I'm going to talk about. This is the chemistry that's involved in my discussion. And the reason this chemistry is important is because it links back to the data that we're given in this particular way. If you set that out at the beginning of your answer, then after that you can go into your more complex discussion about all of the things that are involved, knowing that you've already made those links. And it does stop you going round and round in circles, trying to halfway through your discussion kind of realize that, I've got to link that back to the question itself. I am aware quite often of examiners' reports that say, and I think we said it in the one we saw earlier today, that the discussion needs to be relevant to the question, which means you have to show how it is relevant to the question. Okay, so what I'm saying here is a way of looking at this is to think about what is the guts of the question that I've got to talk about. So because this is about discussing thermodynamic factors, the thermodynamic factors is going to be my explanation for the difference in the solubilities. And what I can see when I read through this is that calcium carbonate, just by looking at the data here, that it's less soluble in water than sodium chloride. So that's what I've got to explain. I've got to come up with a reason based on the chemical principles. So I'm told this. In a way, when I say I'm told that is, if you like, a reflection of the data that I'm given here. Okay, so I can see I'm interpreting my KS data to say that this is much less soluble than this one. The other data that I'm given is about the enthalpy of dissolving. So the enthalpy of dissolving calcium carbonate is negative. The enthalpy of dissolving sodium chloride is positive. So although calcium carbonate is less soluble in water than sodium chloride, the actual enthalpy of dissolving here is exothermic, whereas this one is endothermic. So I then look at that data and I recognise that it's got to be to do with entropy, because if the dissolving process is going to occur, the entropy total has to be positive. It's got to be greater than 0. Now, you don't have to use these symbols, but it's helpful. You could just talk about entropy. You could talk about change in entropy, which we've done there. The total entropy change has got to be greater than 0. Now, then it might be helpful at this point to put in the underlying, how that claim here about the dissolving process being spontaneous, let's link that back to the things that we're given here. So here I'm putting out that my discussion here is going to be about how the entropy total is made up and how that links back to the data I'm given. So I here have a spontaneous, if you like, the dissolving of sodium chloride is spontaneous, dissolving of calcium chloride is not. So delta S total for one is going to be positive and for the other is going to be negative. But the delta S total is related to the delta S of the system and the surroundings. And the thing is, if the delta S total is greater than 0 and one of the others is less than 0, then we must have some compensation for a negative delta S to allow the total delta S to be positive. Now, this may not be the most useful way for you of actually interpreting this or saying it, but I guess what I'm saying here is let's put at the beginning what the basis for our discussion is. So when somebody comes to look at the answer to your question, they are aware that you understand that the dissolving process is related to the total entropy sign, and that the total entropy is related to two things, systems and surroundings, and that somehow from the data that you're given, you're going to be able to explain this. Okay, so I put it out there at the beginning. You might put this somewhere else in your discussion, but that's really the guts of what I'm going to be talking about. Okay, so the examiner knows that I know something about how to put this together, but then you have to show how it goes together. So my discussion points would be, firstly, let's go back to the data that we're given, which was about the delta H of solution, and let's link that to delta S of surroundings. Okay, so here's something that you know about, don't you? You know that as you change the temperature, so either if it's exothermic or endothermic, that's going to change the surroundings. So if it's taking heat from the surroundings, then if it's taking it away, then it cools down, it becomes more ordered, so that's going to change the sign. So you've got to do that. I'm not going to do it all for you today. We don't have time for that. And then we're going to talk about how our delta S, then we're going to talk about how we can predict the sign of delta S system for each salt if we already know the connection between delta S surroundings and total. Okay, and then this is really probably the toughest part of this one here, and maybe one of the tougher parts of this paper. You're going to compare the factors that contribute to the differences in the delta S system. So this connection here is something that you're used to doing. You do this quite a lot in your level 3 discussions. Here it's a little bit trickier because you know whether it's spontaneous or not. Your delta S surroundings might be negative, and therefore that tells you that your delta S system has to be positive, or it might be the other way around. So that's the sort of discussion that you're going to need to have. And what I suggest you do is that you look up the answer from the assessment schedule after you've tried to write this yourself, and you have a think about whether you've put all these things together in a way that is logical. There's a couple of things that I just wanted to mention here because they're not things that you will know coming from level 3, but they might be things that you could think into if you can have a picture in your mind of what's happening when you dissolve salts. So delta S surroundings you're okay with because you've done it before. Delta S for the system. So when you get through all of that discussion I've been talking about, you'll recognise that for sodium chloride it must be positive because delta S surroundings is negative. For calcium chloride, it's going to be the other way around. So our dissolving process always is going to increase the entropy of the solute because you've got more particles in there. So there are more particles, so there's going to be more randomness of the particles within the solute. Okay, because that's the stuff that you've put in. However, the entropy of the solvent is actually going to drop. So your water molecules, your water particles, they're now going to start lining themselves up around the ions. You think about that thing you used to draw for level 2 when you were dissolving a salt. So you've got your water molecules lined up around them. So that the randomness of the water molecules actually drops when you put a solid into solution, when you've got your ions separating out. So what we're saying here is that overall, our dissolving process for NaCl is positive and for calcium carbonate is negative. The same thing happens for the solute. So why is there a difference for what goes on in the solvent? And the difference must be related. The only thing, okay, you have to sort of extrapolate the ideas here. There is a difference. Why is there a difference? The only thing you can see here is going to be related to the sizes of the ions, isn't it? So here you've got Na plus Cl minus. Here you've got Ca2 plus CO3 2 minus. These ions are much bigger. So therefore, they are going to be attracted to a lot more water molecules. So the amount of the randomness of the water molecules drops even more for calcium carbonate than it does for NaCl. Now, you may not get that. This might be something that most of you would not think to see as a way forward for this. But don't panic. Okay, go as far as you can with this. You might just be able to get to the point where you can say this. And you may not be able to give a reason for it, but write down what you can about the connections between this equation. I like to work from this equation. You don't have to. You could just use the words. But if you're working from this equation, it gives you a systematic way of exploring each of these things. How this relates to the changes in the equation for whatever's happening, how this relates to delta H, and how that links back to here. So that's kind of quite a nice way of getting a logical explanation about the overall entropy, but then how you describe the different the changes in the delta S system may take a little bit more exploring. So get something down there. And then this is kind of like you like the icing on the cake. I hope that makes sense. It's not necessarily an easy one to come up with a nice straightforward statement here. And that was as good as I could get for it. You might be able to come up with something better. Okay, let's just finish this one off and then let's just take a break. I'm kind of losing track of the time here. How are we doing? Okay, we'll take a break after this because this is a shorter one. Draw all the potential three-dimensional structures for the IF2O2 minus ion. So here they are. I've done it for you. I think you probably would all have come up with something like this. You will have worked out, come up with the Lewis structure that required you to end up with something that is going to be have a trigonal bipyramid shape of your 5-electron clouds. And then you're thinking about the fact that you've got O's and F's. And so there's a variety of ways of drawing them. Now, don't be put off by the fact that there are double bonds here. If you go through the Lewis diagram methods that you've been taught, then there's nothing to suggest that you need to draw double bonds. You can still come up with exactly the right answer for this question without the double bonds. So don't worry about that. They just happen to be double bonds, and there are reasons for that are beyond what you have to know. So if you draw single bonds, that's okay. It's still relevant to the answer. Okay, so here we have it. And again, it's an explanation type question for part 2. We've got our 5 possible arrangements of 4 bonds and a lone pair. And then make sure you get out there what is the basis by which you're going to explain whichever one you choose to be the most probable arrangement. VSEPR, you may not have heard it called that, valence shell electron pair repulsion. That's what you're going to talk about. Okay, so you've got the repulsion of the electron clouds, regions of electrons. It's not really just pairs of electrons if you look at the picture here, because you've got double bonds. So that's why I like the idea of regions of electrons. So the most likely arrangement will have the electron clouds with the largest density in the plane. Why is that? Because the electron clouds on the central atom are arranged to minimize repulsion. And so the connection to this diagram is that they will have the largest angles between them. Okay, so I've put out there what the basis for my discussion is. I've got my data. It's about how the electron clouds are arranged. And the reason for that is to minimize repulsion. Okay, you should be able to click on, you should be able to follow that based on your level 3 discussions. So what's going on here? Well, it's to do with the size of the electron clouds, and I've got some quite useful data in here about the relationship between lone pairs, double bonds, and if you didn't have double bonds, it's still okay, because the bond to an atom of lower electronegativity is greater than the single bond to an atom of higher electronegativity. Excuse my bad misspelling here. Okay, so you didn't have to know that. Here you're interpreting the data that you were given in the question. So in my trigonal bipyramid arrangement, well, there we go. There's my discussion. And you can come up with something for yourselves once you know what you're going to link it to. And I'm sure that you will have got there with that one if you recognized what you had to do here. I think you're okay with lone pairs, aren't you? Because you've done that before. You recognize that in your trigonal bipyramid arrangement, you've got 2 different bond angles, 120 in the plane, 90 degrees in the plane to the axial positions, and therefore the 120 degree ones angles will be available for the largest electron clouds. So there we go. We're going to come back and look at question 3 in just a minute. I think we'll take a break, and if there's some questions, I'll address them before we move on to question 3. Hope you're still with us. Just maybe 2 minutes just to grab a drink of water, maybe get some fresh air, but just clear your head of everything we've done so far, because we're going to come back and look at question 3 in a minute. Cool.
Should we come back at 11:15? It's now 11:11.
Yep, sure. Okay. Yep.
Cool. And there's some questions there, but we'll answer them when we get back.
Okay, that sounds great. Thank you.
Cool.
Okay, we're ready to go again?
Yep. Yep. I'll just go through one question.
Yep.
Do you know if we have to gain the precursor grades to gain the outstanding ones, i.e. get like 1 scholarship mark but 2 correct outstanding calculations?
I
assume to get outstanding scholarship you need to get everything. That would be correct.
You just have to get, well, I think I had on one of the early screens the numbers. I think it's a numbers game at outstanding level. I presume you'd have to have at least 1 at outstanding. But so you 25 out of 32. So, you know, that was from last year's, and I think it's been reasonably consistent. So that's 7 marks that you've dropped over the whole paper. So if you think about all the combinations that you could have to get 25, you'd have to have at least 1, 7 or 8 to get outstanding.
Cool. I think that's hopefully answered that question.
Yeah. And it would probably vary from year to year, but they do have a percentage that they're looking at to try and get, and it's reasonably consistent. I haven't got the stats in front of me now, but I do have them somewhere. Yeah. Does that help?
Yep.
Hopefully, come back to me, whoever wrote that, and I'll have another go at it and show you the stats if you like.
Yeah. Right. I think that's it for now. We can continue on.
Yeah. Okay, cool. Right, we're up to question 3. We've got 2 to go. So let's motor through these. And I'm not going to dwell too much on the first part of this question, but what you'll notice is there are actually I've lost it here. I think there might just be 2 parts to this question, or maybe we'll see. Maybe there is another part to it. What do we do? Okay, let's go anyhow. Part A. I've noticed this sort of happening a few times in scholarship where you're actually required to work out from some data that you're given what is the empirical formula and then the molecular formula for a given compound, and then taking on board some information that you're given and then draw some structures from it. So there was also an example in this year's mock exam for chemistry scholarship that you might like to go back and check if you've done that before. So the reason I just want to sort of mention these ideas is that often this particular chemistry calculation is overlooked now that achievement standard 2.2, I think it is, or it might be 2.1, is focused more on the titration and volumetric analysis, and some of the other calculations around moles have not always come to the fore. So if you've never done or you haven't had a lot of practice at these type of calculations, then I will go through it fairly quickly, but you might need to find other ways of practicing it, and some old level 2 questions or books will help you there. Okay, so this first one is just trying to figure out some structures, but you kind of realize here that we're coming into the realm of organic chemistry, and down here we've now got something about alcohol. So this is very much our organic chemistry and a little bit of NMR data down here as well to figure out what we have to use. Okay, so here, formula structure, organic structure, but when we get to here, we find that we've got to talk about here about a distillation process, and we've got some compounds here in our final mixture, and this is actually our intermolecular forces question. Well, this was a bit different really from what's happened in the past, because usually you're given maybe 2 or 3 or 4 compounds and you're given some data about them and you're asked to explain why they have different melting points or boiling points. think you had one like this in level 3 yesterday, didn't you? Where you had 3 different compounds and you had to come up with reasons for the difference in melting and boiling points. Again, I don't think I've ever seen a scholarship exam that hasn't got some discussion about intermolecular forces. But here, it was right in the middle of an organic chemistry question. So don't be fooled. You have to still find a way through that. And then a little bit of a reaction. Okay, so let's have a look at what we've got here. Okay, so there was only parts A and B in question 3. So let's see what we can do. Part A, we have a compound. We've just called it X. We've got some elemental analysis. In other words, this compound was made and then it was probably burnt off or something, like it's got a complete combustion reaction here, to try and figure out how much of each of the elements were present. So we could find out the mass of each of the elements present, and that, of course, will allow us to find out the moles of them. Then we've got a bit of mass spectrometry in here, and that will be helpful in terms of determining the molecular formula that we have. Okay, so determine a molecular formula. This is just me trying to download the information. You may not, in a short question like this, necessarily have to do this, but here's my thinking. Okay, that's what I've got to do. I'm given some combustion data. Now, what I've done here is I've kind of just vaguely tried to use some symbols that are helpful for me. This is nothing that you would normally find in a paper discussing something in chemistry. This is my shorthand. Okay, I'm going to use this combustion data in some way. Now, this is what I would be thinking about doing, because I'm used to determining empirical formulae and molecular formulae. You might just think, I've got some masses here. I have no idea what to do. Let's change them into moles. If I'm going from mass to formula, I've got to get a mole ratio. So start there, even if it's not it's not so obvious to you how you're going to get your final answer. So if we've got masses, let's use it to get moles and then see where we go. So I did this. So I've taken worked out the moles of carbon because I know the mass of carbon dioxide. So that told me the moles of carbon. That means I can work out the mass of carbon. I can do exactly the same with the working out the hydrogen, because I know the mass of water, and I can link that back to the moles of hydrogen. That will give me the mass. Now, I'm just saying this very quickly. I suggest you come back to this and think it through more slowly if you're not familiar with these. What about oxygen? Well, if I've worked out the If I've worked out the mass of each of those, I worked out the mass of each of these, then whatever's left over has got to be oxygen. Whatever's left over from the stuff I started with, and therefore I can work out the moles of oxygen. Right? So that's a good start. So what's next? If I've got a formula, I want to know the mole ratio of carbon to hydrogen to oxygen. So I've taken the mole ratio, I've divided through by the smallest number. So that means that if I divide through by the smallest number, that changes that one to 1. It makes this amount of the ratio of the hydrogen present 5 and the carbon present 2. So my ratio of carbon to hydrogen to oxygen is 2 to 5 to 1. This is my empirical formula. It may not be the actual formula of the molecule, but it is the ratio of carbons to hydrogens to oxygens. How do I know the molecular formula? Well, I look at the molar mass of the empirical formula and I compare it to the mass that I got from my mass spec data, which was 90. And I realize that this is twice as much, and therefore my molecular formula is C2H10O2. C4H10O2. Okay, so that's a quick a little discussion there of empirical formulae and molecular formulae. If you're a bit rusty on it or not familiar with it, go back and think about what I've done and why, and then maybe look for some questions that give you a chance to practice other ways of doing that. Okay, second half of the question, what you're told is that X is produced from W, which has H plus and MnO4 minus. And so you're recognizing that. Well, let's go back and have a look at X. I've got some answers there I didn't mean you to see. Let's have a look at X. it's got 2 O's. So 2 O's suggests to me, functional group with 2 O's could be an acid functional group. But here I've got a compound there where every carbon is saturated. There are no double bonds to carbons here because I've got 10 hydrogens. Okay, so it is a saturated molecule. And so that suggests to me that it is likely that I have got 2 OH groups. And so the first thing I've got to do is just come up with with diol structures. So 2 OH groups, 4 carbons, and I know that X comes from reacting W with permanganate. So I know that permanganate reacts with alkenes to oxidize them and to produce a diol. The permanganate, when it's in the presence of H+, will do that. Okay, so what have I got? Here we go. I can draw those 3. And remember, it's a diol that is coming from an alkene, so therefore the OH must be present on adjacent carbons. So there are other ways that you could write a diol that has 4 carbons, but the OHs must be on adjacent carbons for them to actually match the isomers that you have described here. Okay, so I'm going through this fairly quickly, but it's just to try and get you're thinking about what's the data that I have to interpret in order to produce these isomers. So the data you have is related to the actual molecular formula and also to the reaction that is going to that comes from your level 2 organic chemistry, doesn't it? Where you've got a double bond that is oxidized by permanganate in the presence of H+ to give you that diol. Okay, so come back and think about that, or go back to that question and see how far you can get. Now I've given you a few clues. How far can you get through that towards the answer with thinking it through from your own knowledge? Okay, so question B. Question B has got quite a bit more to it, so probably there's a half an hour maybe involved in this one and quarter of an hour involved in part A. So we have compounds E to H, so there's just 4 of them. They're alcohols. They naturally occur, they're in a mixture together. You're told that they are isomers of C4H10O. There's quite a lot of isomers, maybe. Addition of acidified potassium dichromate solution, followed by gentle heating. So again, already you're thinking, okay, I've got acidified dichromate with alcohols. So that does actually limit the number of possible structures that I can draw from this. I heat it gently, and that results in the formation of a variety of new organic compounds. Under these conditions, not all the compounds are fully reacted, and the final mixture contains 9 different organic compounds, E to M. So that means that all 4 of those alcohols are still present. Some of them have reacted to varying degrees to create some new products. And then the mixture was separated by distillation. So the first thing to do is to get the structures. The second thing is to go back and think about this distillation process and how come it works. How can I actually separate those based on the distillation, based on my understanding of the structures of the molecules? And then the last question requires me still to know what those 9 compounds were and come up with something, a new molecule based on the reaction of 2 of the things in there. Okay, so I've got I've got my alcohol isomers that are oxidized, and I recognize that I'm going to make some products that are dependent. So my thinking is, as I'm going through this, is that these reaction products, how come I can get another five products out of 4 molecules? And that's because it's going to be dependent on the position of the OH group, isn't it? So my primary, secondary, and tertiary alcohols all respond differently to the reagent that I've put in. And there are some steps along the way for my primary alcohols. So my primary, aldehyde to acid, because I've been told the reactions don't all go to completion, and my secondary alcohols will go to my my ketone. So let's go. Let's see what we can do. Oh dear, I've got some other words in there that you weren't meant to see yet, but don't worry about that. Let's look at the possible alcohol. So you can have a play with these. Let's just comment, because it wasn't too hard to do these 4, was it? But if you've got a bigger carbon chain, learn to be systematic when you're asked to draw all the isomers, or where you need all the isomers to try and select the right one. Go for the longest chain you can. Look for the different positions of the functional group, such as I've done here. Then shorten the chain by 1 by putting in branch chains, and then look for the different positions of the functional groups. Okay, you didn't need to do that here. It was more simplistic. But if you've got 5, 6, 7 carbons, it becomes more that you have to be more systematic to be sure you've got all of them. Right, what possible reaction products can I get out of this? So let's go systematically through our thinking. Primary alcohol, our products, there are 2. We can get the aldehyde, or we can get the carboxylic acid. We have a secondary alcohol, so we'll make a ketone. We have a primary alcohol, so we've got 2 possible products again. And we have a tertiary alcohol, so there are no products. Again, this is nothing different from the chemistry involved in your level 3. It's just that there's a lot more happening than you would normally have in your level 3 questions. Maybe not. Okay, here we go. So there's your products. You weren't asked to name them. That was as much as you were asked to do. The second thing we have to do now is we have to use whatever labels we have here to discuss the chemistry involved in the separation of the compounds. So what have we got? This is our discussion question now. We've got to think about how we're going to present it in a logical, concise way, and make sure that we link our discussion and our chemical principles back to what is actually going on, what is observed, what is going on in this distillation process. So let's think about the distillation process. We separate the particles, the compounds rather, because they have different boiling points. Okay, it's not a nice question which says discuss the difference in boiling points. You had to figure out that that's what you were going to do. Why have they got different boiling points? Because they've got different functional groups and different structural arrangements. So when you go to do your discussion, you're saying at the beginning that that's what you're going to talk about. Why? Let's make a link in here so we don't have to come up with this later or halfway through and say it lots of times. If we have an increase in boiling point, as the boiling points get bigger, we have stronger intermolecular forces. Now, in a way, I think maybe I would like to put another word in there. The total intermolecular forces are stronger. Because remember, your intermolecular forces are the net forces operating. They're not just hydrogen bonds. They're not just dipole-dipole. Every compound has instantaneous induced, we normally call them temporary intermolecular forces. And then if there's a dipole, you also have the dipole-dipole intermolecular forces, and the hydrogen bonding is an extension of that. So you do need to be thinking about the total intermolecular forces, and as they get stronger, you have increased boiling point related to the functional groups and the shape of the molecules. And why are we going to even talk about intermolecular forces? Because as they get stronger, you need more energy to separate the molecules. And so the ones that have the weakest intermolecular forces, I've said here, you could do it either way around, will boil off first during the distillation process. So I've actually talked about the distillation process and talked about its connection to boiling points and connected the boiling points then to the intermolecular forces discussion I'm going to have. So this is what I'm presenting at the beginning of my answer, and then I'm going to go through step by step and look at the groups of molecules and their different intermolecular forces. Okay, so you're probably okay about doing what I'm going to put up here in purple, but did you stop to think about how your answer is going to come across in terms of its connection to the process and an overview of why intermolecular forces are important? Just keep that in mind and then make sure you can do this. Now, I've started with the strongest. It doesn't matter how you do this, but I've often found with intermolecular forces, it's quite useful to group things. If you've got 4 things to discuss, you might need to do them in pairs. Sometimes even with 3, it might be comparing the first 2 and then comparing the third one with the first one or with the other 2. There's various ways of doing it. Just make sure you've thought about how you're going to put it together so you don't have to say the same thing over and over again. So I've started by saying, let's look at the acids, and I recognise that they're going to have the highest boiling point for a couple of reasons, actually. And I realised as I was coming towards this morning that I forgot to put the second thing in here. So if you look at your acids, which are J and M, the acids are going to have a higher molar mass than the other compounds, and therefore the temporary dipole forces are going to be higher for those, and so that should be added into this answer here. So there's 2 things about the acids. One is that they have larger temporary dipole forces of attraction, and so that is going to increase the overall net force of attraction, and they also produce more hydrogen bonds between the molecules than is the case for the other things you have in this mixture, which are alcohols and aldehydes and ketones. So you're going to talk about why they have this is just, all I've made here is a few notes. You obviously will develop this into sentences. So there are more hydrogen bonds possible. I suggest that you say more hydrogen bonds between the molecules possible, because you want the examiner, the marker, to know that hydrogen bonds are between the molecules, and you've not just got this learned thing that I must talk about hydrogen bonds, but I don't really quite understand them. So recognise that the hydrogen bond is the bond, the intermolecular force, it's 10% of the strength of a covalent bond, and that's the force that attracts one molecule to another through the OH that you have on one molecule, through the hydrogen of that one molecule to the oxygen of the OH group in the other molecule. There is also the potential for a dimer with the carboxylic acids, and if you have a look at the model answer for this in the assessment schedule, that dipole is listed there. The 2 intermolecular forces forming the dimer is listed there as another reason. So add that in and have a look at that in the model answer. I can't cover everything today, I'm afraid. Okay, the other thing to note here is that your 2 acids, although they're both higher than everything else, one is going to be higher than the other, and that is because your straight chain acid, which is J in my list, is going to have a higher boiling point than your branched chain acid, because these molecules are not able to get as close together. So I would normally talk about that they don't pack so well. You can pack these ones. Remember, this is a zigzag molecule, but they still pack together more easily than when you've got a branched chain coming off the side. So quite often the language of the examiner over the last few years has been that if they're branched chains, the molecules can't get as close, and so therefore the intermolecular forces are not so strong. So we've recognised the acids are the highest, but that the straight chain are able to get closer, and therefore J is higher than M. Okay, so I'm not going to dwell on the rest of these. I've then talked about aldehydes and ketones being the lowest, and recognize that's because they are unable to form the hydrogen bonds. Remember, they are all polar, so they still have dipole-dipole attractions, which are added to their temporary dipole-dipole attractions, but they are not as high as the other 2 because they are unable to form hydrogen bonds between the molecules. There is some extra here about why that ketones and aldehydes are slightly different, and then you also have the aldehyde that is a branched chain, which is going to be different from the aldehyde that is a straight chain. If you could just look at the aldehyde compared with a ketone and say that they are similar, but the aldehyde has a slightly higher boiling point than the ketone, and there's a vague reason for that there. Just say that they're similar. Don't be too worried about trying to separate those out if that's the limit of your understanding there. And then a little bit at the bottom about alcohols, and recognizing again the straight chain, with the alcohol at the end of the chain being different from the alcohol that's partway in the chain, primary being stronger than secondary, and tertiary, of course, with its branch chain there being harder to pack. So I've given some vague, not vague, but for some fairly brief notes there about the things that I would include in my discussion. I guess my major point here is plan it. Think about how you can introduce your discussion, and then think about how you can group each of these things, and then within each group expand what you have to. It's practice at putting together these answers that will make it much easier for you when you get to the exam to actually think about how you construct your answer. So please take time, not necessarily to redo this one, but maybe this one would be helpful for you to try and think about the words that you're going to use and how you're going to explain it. Don't just look at it and think, oh yeah, I know how to do that. I know what I'll say. Practice what you will say, how you will put it together, so on the day you don't get too waffly. You've already got a concise way of putting these ideas together. Okay, hopefully that's the longest one I'm going to have, because otherwise we're still going to be here at 12 o'clock. Right, here we go. The last one, the possible products to create this new molecule. You've got a little bit of NMR data here. The NMR data relates to the number of peaks. That's going to tell you what possible combinations you can have. But please, just fairly quickly, please note that you didn't just have to come up with the structure. You were asked what the conditions were, and you were also asked to link it back to the carbon-13 NMR peaks. So, you might have been really delighted to come up with your answer, which was this. But what's that got to do with the two things you were asked to do? Well, look, I've shifted that slightly. Just ignore those ones there. I've actually just sort of come up with a colour code here that will link that back to the number of peaks in the IR. But you think of a way of doing that for yourself, and then make sure that you can make that connection and that you do talk about the conditions. Okay. Let's get going. Let's get on to the next one, and I'll ignore that slide because you can look that up for yourselves. Right, last question. What's this about? Whew. We have maybe some things that you're not all that familiar with, but that's okay, because you can still work with the ideas that are here. And if you look at part A, let's just skip to the last part of part A. 3 parts to this question. Last part of part A. Account for oxidation and reduction processes, write balanced equations, and use oxidation numbers. So here you might have done this found this earlier in the paper and thought, I'm really good at oxidation numbers. Let me get onto this and get this done because I know what I'm doing. So there you go. But remember, you're using oxidation numbers to justify oxidants and reductants. Part 2. Okay, the thing that stands out to me as I read through this is this word Hess's law keeps popping up. And so a little bit of thermodynamics. Now, there is a whole lot of data included in the question, which we'll come to in just a minute. And the last one, here I have some isomers and some spectra. Actually, the thing that would have triggered you to realise this was somewhere in the paper was looking at that resource booklet where you had the IR data and the NMR data. It's right there at the very end of the paper, but this might be something that some of you might enjoy doing from your spectroscopy standard. Okay, so let's get into it. First one, a whole lot of words and some symbols. And so I've got a story here that I have to kind of figure out how I'm going to get the balanced equations out of it. So here we go. I'm going to write balanced equations. I'm going to work out oxidation numbers, and I'm going to link those to oxidants and reductants. So look what I've done here. I've not written balanced equations. I've started off by just writing down the formula for what's going on. So my first reactions, this is in part 1. I've got my thiosulfate. Look, I've ditched the sodium. I'm really just interested in the iron. And I made colourless sulfur dioxide gas, and I got this yellow solid. Okay, so a bit of a guess. It's probably sulfur. What else could it be? If I've got thiosulfate hydrochloric acid, can't come up with much else. So that was, sulfur. The second part of the second reaction, what I've done is I've taken nitric acid. Okay, I'll keep that in as nitric acid. And out of that, I got NO2, and I got the yellow solid again. Keep reading, because I also got sulfate ion. So here what I've done is just written some symbols. Once I've got the symbols, it allows me a moment to actually think about, what's going on? I'll just go back out of that just for a minute, because let's have a look at it. If we look here, it gives us a whole lot of clues. That's why I like interpreting or writing equations to interpret all those words. Because until I wrote the equations, even these vague ones, which are not balanced, I wasn't really quite sure where I was going to go with this. But then I can look at this and see that the HCl, I've got no products related to HCl, because I can't get a yellow solid out of that. But the thiosulfate has actually changed it's into two different things, sulfur dioxide and sulfur. Right, let's do this in terms of oxidation reduction. Here I've gone I've actually lost a whole lot of oxygen to go down to this. So this must be this is very simple terms. This is reduction. It's me getting my head around it. And so this is oxidation. So my thiosulfate ion has actually been both oxidized and reduced. Okay? And then if I go to this one, my thiosulfate ion, again, look at this. It's been both, I think, perhaps it's been reduced. Maybe it's also been oxidized. And at the same time, my NO3 minus ion has changed to an NO2. So it looks like this has been reduced. So two reduction reactions going on here, one oxidation. Here I have my thiosulfate actually changing into two different oxidation products. So we call this a disproportionation. Sometimes that word has been used in scholarship. Doesn't really matter, but it's the one thing undergoing both oxidation and reduction. Now I've done that, I've got an idea as to where I'm going to go with this. And due to our time constraints, I'm not going to slow down and work through this for you, but that should give you enough now to be able to formulate an answer. Just go through it systematically. The first thing you would do would be to write your balanced half equations. Okay, so let's take our thiosulfate becoming sulfur. Let's take our thiosulfate becoming sulfur dioxide. And now you see why you needed some acid in there. It was nothing to do with the acid being oxidized and reduced. It was because you needed acid for the oxidation and reduction processes. Whoops-a-day, sorry. Okay, once I've done that, I've got my overall, and then I can start talking about my change in oxidation state, and I can relate it to my oxidants and reductants. Okay, so I probably haven't even done that here. I've just talked about the change in oxidation state. You would need to go back and make sure you justify the changes related to what is meant by oxidant and reductant. So just make sure that you're pretty good at oxidation numbers, because you may not have really even thought about them since level 2. And I've seen them come up a few times in scholarship, usually around this sort of question. Okay, and then the second one, a little bit trickier, because in the second one, you've got your balanced half equations for thiosulfate, but what you notice is that in the first one, you had the same number of electrons lost as gained. In the second one, you need 4 electrons here, you lose 8. So where am I going to get the rest of the electrons? They must come from the nitrate. So that gives you a clue as to how much nitrate you need when you go to put to combine your 3 equations. So a little bit harder, a little bit more thinking, but if you actually sort of thinking into what's going on as the reaction occurs, you can see that you don't have enough electrons. When you combine these two, you need them to come from somewhere else. So this is where they come from. Tell yourself the story. Think about what's going on and how you can then package that to come up with your answer. Okay, So again, once you get started with this, once you can get the equations out of the words, even though you weren't really sure where this was going when you first read it, those equations now lead you into something that you are familiar with. And even if there's a bit of a twist in number 2, or even in number 1, where they both go to where the same iron is both oxidized and reduced, it's not totally unfamiliar. You've got enough skills to be able to do that. You can do it. Okay. Question 4B. Hess's law. Again, just couched in a different example, if you like, of how you can combine a number of different pathways to get to the actual reaction that you're after. So here it's kind of a bookwork thing, isn't it? Where you're looking at the equation that you want, the reaction that you want, and you're thinking about a whole lot of possible steps that you actually know the data for that will add up towards that. So do it using the same kind of systems. When you've given a Hess's law, look at the equation that you want and think about the combinations of the equations that you're given that will add up to that. So again, there's a lot of words here that may or may not be helpful for what you're trying to do. Because you don't know what lattice formation enthalpy is, the examiner has needed to define it for you and then has given you an equation. And so this is the guts of what you need to know. What you're asked to do, let's have a look at what I've got here. What you're asked to do is you're asked to calculate an enthalpy of formation. Now, you're not given the equation for that. So what you need to make sure you can do is write the equation that links back to the data that you're given. Again, a little clue, a little hint here is to keep in mind what you're asked to do. Don't just calculate that. Sure, you're going to use Hess's law. Remember that you have to do the comparison to the existence of CSF, which is what we would expect to get. CSF2 is not something that you would recognise as being a likely ionic compound, and we can think why in a minute. So here's my equation that relates to the enthalpy of formation. So that's what I'm after, and I'm going to use all of this data to somehow come up with that. And then I'm going to do my discussion. So how did I put it together? Okay, again, I haven't quite got this in the form that I meant to. Here we go. This is what I'm after. And then you can, as you've probably found in the other questions like this in level 3, you sometimes can just use the data as it's presented to you. But let's think about what this means. I'm starting with the solid cesium. First thing I can do is make a gas. Then I can, from the gas, I can create the ions. You've seen this equation before. It's ionization enthalpy, isn't it? In this case, I needed CS2+, so I need the second ionization enthalpy. Did you notice that the second ionization enthalpy is much bigger? So it's much harder to take the second electron away. I wonder why. With the fluorine, I'm going to need to create 2 fluoride ions. So I've separated out the fluorine, the atoms from the molecule. I've created 2 ions. I've just bolded this to remind you that you had 2 Fs here. You need 2 F minuses to create your cesium fluoride 2. And so you had to double that. That's the only thing that you had to change. And then the last thing you need here, because I've created 2F minus, I've created CS2 plus, I've used up all the electrons, and then I needed this bit of information that I had in the question in order to be able to put all of these together and come up with the answer I had. So that was what I was after. So, okay, you can come back and do this in your own time, and you get a delta, something here that is endothermic and quite small. So if we compare that to the delta F for calcium fluoride for CSF, we find that that is minus 554. We're actually given that in here. So that's the enthalpy of formation of calcium fluoride, cesium, I should say, fluoride, is minus 554. So we kind of expect that this is going to be much more likely than this one. So where's the difference? And the difference is that for CSF, we didn't have to carry out the step here. We didn't have to create the CSF2, and that required a lot of energy. We also only needed one of these, but then that's a negative, so that's not going to actually favour the formation of CSF. It's not having this step. So why do we need to put in more energy to take the second electron off? And so therefore you need to go back and think about what electron are you removing. So if you think about where cesium is in the periodic table, first electron is in, has a valency of 1. Okay, it has 1 electron in the outer shell. Once you've removed that, the next electron you're removing is much closer to the nucleus than the first one that you took out. And so therefore you could maybe then talk about shielding and the distance from the nucleus, as you know from your level 3 atomic properties. Okay, so really your Hess's law should not have been too much of an issue if you could figure out how to use the data that you're given. The issue might be in thinking about just what's going on that's different between these two. Not something you expected to know, something you should have been able to work out, or you could have perhaps worked out from the data that you were given. Okay, and then after that, you were also asked to compare the lattice enthalpy of the two different ions. Why is this one here much bigger than this one? And so I'm just going to tell you what the answer is, and then you could think about how you would explain it. So if you look at this, if the lattice, think about, and again, here there's some good chemistry you could write down, even if you couldn't come up with the whole answer. What I'm doing here is I'm actually creating a solid from the ions, and I'm releasing a lot of energy, and that's because I've created this ionic bond. So this is really a reflection of the strength of the ionic bond. So energy is released when I create a bond. Energy is needed to break a bond. So I release energy when I create this ionic bond. I release a lot more energy because the ionic bond is stronger. So what you really need to explain is, why is the ionic bond stronger in CS2 fluoride as opposed to CS1. Now, we don't talk a lot about the strength of ionic bonds in level 2 chemistry or level 3 chemistry, but you can kind of work it out, can't you? Because the strength of the bond is going to depend on the strength of the attraction between the particles. So why do I have a stronger attraction in CS2 when CS2 plus is present as opposed to CS1 plus? Well, the charge is bigger, so it kind of makes sense. The other thing, remember, the strength of the bond, we've talked about this before with intermolecular forces, it depends how close the particles can get to each other. And my CS2 plus ion is smaller than my CS1 plus ion. That should be a 1 plus, sorry. I'll fix that before I publish these. Okay, so this is going to be smaller and it has a higher charge, therefore the bond is stronger. So if you recognise it in terms of the strength of the bond, then you can relate it back to the lattice enthalpy. So you could write down some of the things you know, and then you can try and construct a good answer that links back to your atomic properties as well. I've said that quite fast. Maybe you could take some time and come back to this and just slow it down a wee bit, because we need to spend our last 3 minutes looking at the last question. So here I'm hoping that you're feeling like you're on familiar ground, familiar territory. You're going to interpret the spectra. How I approached this was that I just went through the spectra and I kind of recognized that I don't actually even know how many carbons I've got in this compound, although there's a clue here that the molar mass is less than 100. I've got to use the spectra. I've got to determine, name, and justify one possible structure for each compound. What you will find is that in the first one, there is more than one possible structure, and I'm not sure about the others. I think there's mostly just one. So go through and don't be afraid to mark up your resource sheet. You could go through and check these, make some notes on there, but do make sure that you translate your markup onto your paper. Okay, so I've just jotted down the things that I noticed on each of these from the NMR, number of carbon environments, what do the different positions of the peak tell me? And I could do that for each of them. So here I can see I've got 4, I've got 3, I've only got 2, and I go back to 3, but the difference between the 3 is that is the actual position of the peak that's further upfield. In fact, the different positions. So I've jotted this down, and I've kind of said what I think might be going on in there. And so here I think I've got a ketone or an aldehyde perhaps. Here it looks to me like it could be an ester because I notice the difference in the shape around that IR position. So I've done that for all of them. And then what I've done, I'll just show you on the next slide, I've tried to interpret what I've got here. So I've come up with a structure, but remember that's not all of your answer because I had to name it, and then I also had to say how the structure links to the evidence. So I'm going to talk about my different carbon environments that I've got here, and I'm going to talk about the ketone or the aldehyde and how that and the ketone and the alcohol, and link it back to what I've got here. Okay, and then for this one, what did I think I had? I thought it was an ester, so methyl ethyl methanoate, and then I can connect that back to the fact that I've only got 1, 2, 3 carbon environments, which is what I said I had, and then I can interpret the actual it being an ester linked to the IR data as well. And then, of course, there is the ester peak that I've got in the carbon-13 NMR. All right, and then let's have a look at compound C. It's a little bit trickier now because I've only got 2 carbon environments. So I'm looking for something that has, and by now I know what my, I've got a pretty good idea of what my molecular formula is. So when I come to this, I'm looking for something with a double bond. I'm looking for something with OH groups, but it is also symmetrical. So there's a little bit of a limit as to where I could put everything for that one. All right, and then the last one, here's my answer. I've finally got myself to an acid, but with only 3 peaks because I have that branch chain on the end there, and I can link that to my data. Wow, that's the end of the paper. So we've got through at 12:01. Hey, that's not too bad, but I know I've talked fast. I hope that I've put in enough things to give you some clues about ways to approach the questions, and enough little hints about some things to do. I think probably the key thing is just not to panic and realise that you do know all the chemistry that you need for this, but it's actually how you actually figure out that you're going to use your chemistry, and you're going to write down, even if you can't figure it out, you're going to write down the chemistry that you know is somehow related to the question that you've got there. There's a few things on the screen about approaching the exam, and I think we've covered most of this. Read the question carefully, check your time allocation, plan your answers. Use diagrams and symbols in your discussions. Link it back to the question. For organic problems, read the whole question first and notice all the data. That last question, coming in with that bit of data about the molar mass was useful, and you needed to tag it back to that. When all else fails, use a problem-solving method. Try and get into the questions, looking at step by step, and have a go at every question. While you're preparing, please practice writing out your whole answers. Don't just think, oh, yeah, I know how to do that. Think about putting your answers together in a precise, concise, logical discussion. I'm not very concise or logical after 2 hours of this, am I? Practice solving problems and get used to showing your working. If you don't ever show it in your practice, you'll forget to show it when you get to the exam. Okay, so think like a proton. Stay positive. You can do this, and good luck. But maybe before we sign off, if there are any questions, Andrew, are there some things that we can address at this point?
No questions so far.
Bamboozled everyone, probably.
Yeah, I'd say so. Yeah, I think most kids will probably come back and watch this probably a little bit slower to try and keep up with things.
I definitely. I think you'd have to do that. 2 hours for a 3-hour paper is a bit of a mission.
Yeah. Right. We might as well call it a day then.
Okay.
Unless you have anything else.
No. I'm looking forward to seeing the paper myself and seeing how it can be tackled.
Cool. Just once again, I'd like to thank you, Suzanne, for spending the time to go through the scholarship chemistry. It's something that I imagine a lot of students will really appreciate. If any of you are still watching, if you have questions, you can put them into the Study It chat. I've linked the previous video in the description, and then I think that's about it. So I think, we'll call it a day.
Cool. Well, good luck, everybody, and enjoy it.
Yes.
I've actually enjoyed putting all this together, so hopefully you can have some fun with it too.
Cool. Haere rā.
Bye.